In the beginning, the universe may have been perfect. Not perfect in beauty or in balance as we imagine it, but in a way far more absolute, perfectly symmetrical. Matter and antimatter paired in flawless opposition, forces united, indistinguishable from one another. Energy spread evenly through an ocean of equilibrium, without fracture, without flaw. Symmetry is nature's highest order. It is the stillness of a scale balanced to eternity, the silence of a mirror unbroken. If the first moment of the cosmos held such symmetry, then nothing should have followed. Matter should have annihilated with antimatter, leaving only emptiness and light. Forces should have remained as one, never splitting into the gravity that binds, the electromagnetism that illuminates, the nuclear interactions that ignite stars. And yet, something broke. A fracture ran through perfection. The symmetry of the first instant shattered. Matter triumphed by the slightest margin over antimatter. Forces splintered apart, each shaping the universe in its own way. Tiny fluctuations disturbed the evenness of the cosmos, sowing the seeds of galaxies, stars, and life. Without that imperfection, nothing we know would exist. The universe itself is a monument not to balance, but to broken balance. Its very possibility depends on the asymmetry of the first breath. But what caused that first fracture? Was it chance, a cosmic accident at the dawn of time? Was it necessity, written into the mathematics of creation? Or does it hint at a hidden law, a deeper principle that governs why something exists rather than nothing? The mystery endures, silent and unresolved. What shattered the symmetry of the first moment? The story of symmetry and its shattering begins not in the first second of the cosmos, but in the human attempt to understand why the universe appears the way it does. For centuries, scientists searched for order, for patterns hidden beneath the chaos of phenomena. What they found was that symmetry was not only elegant, but essential, a guiding principle that seemed to govern both the smallest particles and the largest scales of the cosmos. Noether's theorem, The Language of Symmetry, 1918, German. Mathematician Emmy Noether revealed a principle that would change physics forever. She proved that every symmetry in nature corresponds to a conservation law, the symmetry of space, that the laws of physics are the same in all directions, gave rise to conservation of momentum, the symmetry of time, that the laws of physics remain unchanged across past and future, produced conservation of energy. This insight revealed that symmetry was not mere aesthetics. It was the foundation of physical law itself, the deep structure beneath reality. To find symmetry was to find necessity. To break symmetry was to alter the rules of existence. The arrival of antimatter just a decade later. Paul Dirac's equations predicted something astonishing. For every particle of matter, there should exist a mirror twin antimatter. An electron would have a positively charged counterpart, the positron. Protons and neutrons would have their opposites. In 1932, Carl Anderson observed the first positron in cosmic rays, confirming Dirac's vision. The universe, it seemed, was even more symmetrical than imagined. Matter and antimatter stood in perfect opposition, locked in balance. Yet this revelation carried with it a dangerous implication. If matter and antimatter existed in equal measure, then the Big Bang should have produced them in identical amounts. They should have met and annihilated, cancelling one another out. The cosmos should have dissolved into pure radiation, leaving no galaxies, no stars, no observers to measure it. But it had not. Matter remained. The symmetry had been broken, the puzzle of the Big Bang by the mid-20th century. Cosmologists realized the depth of the puzzle. If the laws of physics were truly symmetrical, the universe should not exist in its present form. Yet when they looked into the night sky, they saw a cosmos overflowing with matter. Every star, every planet, every living being was evidence of a broken balance, proof that matter had gained some slight advantage over antimatter in the first moments of time. How? The answer could not be guessed. It had to be sought in the hidden details of nature's laws, in experiments that probed the most fundamental particles. The shattering of parity in the 1950s. A quiet revolution arrived from nuclear physics. For decades, it had been assumed that nature respected parity, symmetry, that the mirror image of any process was equally possible. To flip left and right, to reverse the geometry of a system, should not alter the outcome. But in 1956, Chen Wu conducted a groundbreaking experiment. She studied the decay of cobalt-60 nuclei and discovered that electrons were emitted in a way that violated mirror symmetry. The weak nuclear force, one of nature's fundamental interactions, broke parity. The mirror was not sacred. Nature could choose that. This was the first experimental evidence that symmetry was not inviolable. The compass of the universe could tilt, however slightly, favoring one side over another. The violation of CP symmetry just a few years later. In 1964, James Cronin and Val Fitch uncovered something even more unsettling. Studying the decay of neutral kaons, they found evidence that the combined symmetry of charge C and parity P was violated. In other words, the laws of physics distinguish not only between left and right, but also between matter and antimatter. This was monumental. For the first time, physics had revealed a crack in the perfect balance between matter and antimatter. If such violations existed, they could explain why matter survived the Big Bang while antimatter vanished. But there was a problem. The measured violations, while real, were far too small to account for the overwhelming dominance of matter in the cosmos. The puzzle deepened. The symmetry had been broken, but not enough. Something else was at work. Symmetry in the cosmos. While particle physicists uncovered violations in the laboratory, cosmologists studied the universe itself. The discovery of the cosmic microwave background in 1965 revealed the universe's earliest light, astonishingly uniform across the sky. Symmetry still held, at least on large scales, but embedded in that uniformity were tiny ripples, fluctuations in density that would later grow into galaxies and clusters. These were the fingerprints of symmetry breaking, written into the cosmos. At its birth, the smoothness of the universe was not perfect. In its subtle imperfections lay the seeds of structure. The entry of symmetry into cosmology by the 1970s and 1980s. Physicists began to suspect that the universe itself had passed through stages of broken symmetry. At unimaginable temperatures, in the first fraction of a second, the four known forces may have been unified into one. As the cosmos cooled, the symmetries shattered, splitting into distinct interactions. Gravity diverged first, then the strong nuclear force, then electromagnetism and the weak force split apart. Each fracture changed the rules of reality. Sculpting the universe we know, the question was no longer whether symmetry broke, but how and why it shattered the way it did. The central mystery revealed by the close of the 20th century. The pieces of the puzzle were assembled, but incomplete. Noether's theorem showed the power of symmetry. Dirac revealed matter and antimatter in perfect balance. Wu, Cronin, and Fitch demonstrated that nature could break those symmetries in hidden ways. Cosmology revealed that the universe's very structure was the product of slight imperfections. Yet, none of this explained the central mystery, why the first moment of the universe, which should have been governed by perfect symmetry, fractured at all. Why did matter gain even the smallest edge over antimatter? Why do forces stand apart, when once they may have been one? The discovery phase left physics with a paradox. The laws of nature appear to love symmetry, yet reality exists because symmetry broke. The shattered balance of the first moment is not an accident we can ignore. It is the very reason anything exists at all. The discoveries of the 20th century had set the stage for wonder, symmetry as the foundation of nature, antimatter as the perfect counterweight to matter, the cosmos itself as a near uniform ocean of balance. But then came the unsettling revelation. Reality does not reflect the laws that seem to govern it. The shock was profound. The universe should not exist in its current form, and yet it does. The very fact of our existence is evidence of a symmetry broken long ago, in ways science has only begun to glimpse. The puzzle of antimatter's absence in the equations of physics, matter and antimatter are twins. For every particle of matter, there should be an antiparticle with identical mass and opposite charge. When they meet, they annihilate, producing energy. If the Big Bang created matter and antimatter in equal measure, as theory demands, then they should have cancelled each other out in the first instant. The newborn cosmos should have dissolved into radiation, a featureless bath of light. And yet, it did not. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That smallest of margins, a 1 in a billion. Imbalance is the reason galaxies formed, stars ignited, and life arose. But why? Physics had no answer. The laws appeared to favor symmetry, but reality displayed a fracture. The betrayal of symmetry, the discovery of parity violation in 1956 and CP violation in 1964 were not curiosities. They were betrayals of what had seemed unshakable. Nature, it turned out, did not treat mirror images as equal. It did not treat matter and antimatter with perfect impartiality. For centuries, symmetry had been assumed to be the ultimate order, the compass of physical law. Now it was revealed as fragile, conditional, even false. The shock reverberated. If the laws of physics could betray symmetry at small scales, perhaps the very birth of the cosmos had been written in betrayal. The first moment marked not by balance, but by fracture. The Higgs and spontaneous symmetry breaking in the 1960s. Another revelation deepened the unease. Physicists proposed that particles gain their mass, not inherently, but through interaction with a pervasive field. This became the Higgs mechanism, later confirmed at CERN in 2012. The Higgs field represents spontaneous symmetry breaking. Imagine a perfectly balanced ball perched atop a hill. Any direction it falls is equally likely, yet once it tips, symmetry is gone, and a new order emerges. The early universe was like that ball, perfectly symmetrical, but unstable. The Higgs field collapsed into a particular state, breaking the symmetry and giving particles mass. Without this fracture, atoms would never have formed. Here, too, lies the paradox. Symmetry is elegant, perfect, but sterile. It is only in its breaking that richness, complexity, and life become possible. The shattering truth, the deeper scientists looked, the clearer the contradiction became. The equations suggested balance. The experiments revealed imbalance. The cosmos existed not because symmetry prevailed, but because it failed. This was more than physics. It was a philosophical wound. Humanity had long equated perfection with balance, harmony, symmetry, but the universe itself whispered otherwise. Perfection would have yielded emptiness. Existence depends on imperfection. The first moment was not a mirror unbroken. It was a mirror shattered, and in the shards lay the seeds of reality. The crisis of explanation, and yet the shock was not only conceptual, it was also practical. The known violations of symmetry in weak interactions, though real, were far too small to explain the cosmic imbalance of matter and antimatter. The numbers did not match. This left physics in crisis. The universe exists because of asymmetry, but the mechanisms we know are insufficient. Somewhere in the first instant, symmetry was shattered more profoundly than current science can explain. The shock is ongoing. Every star is a reminder of ignorance. Every breath of life is proof of a mystery unsolved. The existential dimension. What makes this revelation so haunting is not only that physics is incomplete, but that our very existence is balanced on that incompleteness. If symmetry had held perfectly, we would not be here to notice it. The symmetry that should have ruled did not. The imperfection that should not have occurred did. Our lives are written in the cracks of cosmic order, in the fractures of balance. That gave rise to matter itself. The shock, then, is double. It is the realization that symmetry is not absolute. And it is the recognition that without its breaking, there would be no stars, no galaxies, no humans to wonder why. The question left behind, why did symmetry shatter? Was it chance, an accident of probability in the chaos of the first instant? Was it necessity, written into deeper laws we have yet to uncover? Or was it something beyond both, a principle that binds reality itself to imperfection? The scientific shock is not simply the discovery of broken symmetry. It is the realization that the answer to that question is the answer to why there is something rather than nothing. The shock of broken symmetry left physics facing its most haunting paradox. The laws pointed to balance, yet the universe revealed fracture. To probe this mystery, science turned to its sharpest instruments, colliders, satellites, detectors, each designed to peer into the fabric of matter and the echoes of the cosmos's birth. What they revealed was a world where symmetry seemed to hold at one level, only to collapse at another. Colliders, and the search for violations, the heart of particle physics, stood the great machines of the late 20th century, Fermilab in the United States, KEK in Japan, and later the Large Hadron Collider in Europe. These accelerators smashed protons and mesons together at near-light speeds, recreating conditions close to those of the early universe. In 1964, Cronin and Fitch had shown CP violation in kaons. Decades later, experiments confirmed that to violated CP symmetry, the cracks in balance were real. But their scale was too small to explain why the universe contains galaxies rather than only light. These results deepened the puzzle. If matter's triumph over antimatter required vast asymmetry, why do experiments reveal so little? Are there hidden processes beyond the standard model? Perhaps new particles, new forces, or undiscovered laws operate in the first instance of time, invisible to us now, but decisive then. The cosmic microwave background, a portrait of imperfection. Colliders probed the smallest scales, satellites mapped the largest. The cosmic microwave background, CMB, first discovered in 1965, became the most powerful lens into the symmetry of the early cosmos. The COBE satellite revealed the universe's astonishing uniformity, nearly the same in every direction. Its temperature constant to within 1 part in 100,000. This symmetry was breathtaking, but it was not flawless. Tiny fluctuations dotted the map, slight differences in temperature and density. Later missions, WOMAP and Planck, sharpened this image, showing that these fluctuations were the seeds of cosmic structure. Galaxies, clusters, and filaments, all trace back to these tiny breaks in symmetry. Without them, the universe would be smooth and lifeless, a featureless expanse of hydrogen. Thus, the CMB confirmed a paradox. The universe is almost symmetrical, but not perfectly so. Its imperfection is the blueprint of creation, the puzzle of Borogenzish. Dominance of matter over antimatter is known as barogenesis, the process by which baryons, protons, and neutrons came to outnumber their antimatter twins. In 1967, Russian physicist Andrei Sakharov outlined the conditions necessary for barogenesis, baryon number violation, processes that allow matter to be created in excess, C, and CP violation, interactions that distinguish between matter and antimatter, departure from thermal equilibrium, conditions in which the balance can be tipped. These conditions set the framework, but the mechanisms remain elusive. The violations seen in experiments meet the requirements in principle, but not in magnitude. The cosmos demands more fracture than we can yet measure. Symmetry, breaking of forces at the highest energies. Physicists believe that the 4 fundamental forces, gravity, electromagnetism, the weak force, and the strong force, may once have been unified. The early universe was a single symmetrical whole, but as it cooled, symmetries shattered. The strong force separated first, binding quarks into protons and neutrons. Then the electroweak force split into the weak nuclear force and electromagnetism. With each fracture, the universe gained new structure, new rules. This sequence of symmetry breaking shaped reality itself, but it also raises questions. Why these breaks and not others? Why these forces, in this balance, allowing atoms, stars, and life? The shattering of symmetry was not random chaos. It was ordered fracture, sculpting the universe in precise and mysterious ways. Hints from neutrinos. Among the strangest of particles are neutrinos, nearly massless, ghost-like, streaming through matter almost unhindered. They were once thought to be perfectly symmetrical, massless, and neutral. But experiments have shown that neutrinos oscillate between types, meaning they do have mass, however small. This discovery hints that neutrinos may hold the key to If neutrinos violate CP symmetry in their oscillations, they could explain why matter prevailed. Massive neutrinos could be relics of processes in the first second of the cosmos, silent witnesses to symmetry shattering. Ongoing experiments, from Super Kamio-Kondi in Japan to Dune in the United States, are designed to test this possibility. If neutrinos break symmetry more profoundly than other particles, they may solve the riddle of existence itself. The anomalies that persist despite decades of investigation, anomalies linger. Some patterns in the CMB alignments, cold spots, unexpected correlations suggest that the universe may hold deeper asymmetries we do not yet understand. Particle accelerators reveal hints of behaviors that the standard model cannot explain. From the magnetic moment of the muon to rare decays that deviate from predictions, each anomaly is a whisper from the first moment, a suggestion that we have not yet uncovered the full scope of the fracture. The growing mystery, the deeper science investigates, the clearer the paradox becomes. Colliders confirm symmetry violations, but not enough. The CMB shows a universe almost symmetrical, yet saved by tiny imperfections. Neutrinos hint at hidden asymmetries, but the evidence remains incomplete. The mystery does not diminish with discovery, it grows. Each new probe reveals the same haunting truth, the symmetry of the first moment shattered, but the reasons why remain hidden. The question unresolved: what shattered the symmetry of the first moment? Was it the collapse of a field like the Higgs, tipping the balance? Was it the behavior of neutrinos, unseen in the early cosmos? Was it the fracture of unified forces as the universe cooled? The deeper we look, the clearer it becomes that the symmetry we see today, in forces, in particles, in cosmic structure, is only a remnant, a shadow of a more perfect order once broken. The investigation continues, but the question lingers, haunting and unresolved. The universe exists because of imperfection, and yet the origin of that imperfection remains one of the deepest mysteries in science. The investigation of broken symmetry had already revealed paradox upon paradox. Matter survived against all odds, forces fractured into four, and the faint imperfections of the early cosmos became the seeds of everything. But as discoveries mounted, the mystery only deepened. The shattering of symmetry was not only the origin of existence, it seemed to continue, echoing through every level of reality, and with each revelation came an unsettling realization. The very fabric of the universe is fragile. What was broken once could break again. The inflationary shattering in the early 1980s, physicists proposed a radical theory, inflation. In the tiniest fraction of a second after the Big Bang, the universe expanded faster than light, smoothing out irregularities and stretching space-time itself. Inflation explained the CMB's near uniformity. It explained why the cosmos looks flat and why distant regions share the same properties. But inflation also magnified the smallest quantum fluctuations, turning them into the vast structures we see today. The lesson was profound. Even the most delicate asymmetries, tiny ripples in a quantum field, became galaxies, clusters, and filaments spanning billions of light years. The entire structure of the cosmos is the echo of shattered symmetry, amplified by inflation's unstoppable surge. The hidden asymmetry of dark matter, yet ordinary matter, the atoms of stars and planets, is only a fraction of reality. Observations of galaxies and clusters revealed invisible mass, outweighing normal matter 5-1. This is dark matter. What if the shattering of symmetry also created it? Perhaps in the first instance, hidden particles were forged, immune to light, detectable only through their gravity. If so, then the survival of matter was not the only outcome of broken symmetry. It may also have birthed an invisible universe, alongside the visible one, but dark matter has never been directly detected. Its nature remains unknown. It lingers as a shadow of symmetry broken in ways we cannot yet measure. Dark energy, symmetry of the vacuumeth. Mystery deepens further with dark energy, the unknown force accelerating cosmic expansion. Discovered in 1998, it acts like a property of empty space itself, a pressure with no source, stretching the universe apart. Could dark energy be another consequence of broken symmetry? Quantum field theory predicts vacuum energy, but it's calculated. Value is staggeringly wrong, off by 120 orders of magnitude compared to observation. This is not just a puzzle. It is a scream from the fabric of reality that something about symmetry vacuum, and existence itself is profoundly misunderstood. The fragility of the vacuum. In 2012, the Higgs boson was discovered, confirming the field that gives particles mass. But its measured mass carried unsettling implications. The numbers suggest that our universe may not be in the lowest possible energy state. It may be in a false vacuum, a metastable condition, like a ball resting on a plateau above a deeper valley. If so, then the symmetry of the vacuum could shatter again. A bubble of true vacuum could form somewhere in the cosmos and expand at the speed of light, erasing the laws of physics as we know them. This is not science fiction. It is a possibility written into the equations of quantum fields. The symmetry that broke once to give us existence may one day break again to take it away. Entanglement and the collapse of certainty. Quantum entanglement adds another layer. Across vast distances, particles remain linked, their properties correlated in ways that defy locality. Two entangled systems, direction and separation, mean nothing. If the universe is fundamentally entangled, then spatial orientation itself may be secondary, emerging only after deeper symmetries shatter. The compass of existence points not outward, but nowhere at all, until collapse makes a choice. This raises the terrifying possibility that symmetry is not just broken at creation. It is being broken constantly in every quantum event, across the fabric of reality. The universe without foundation as inflation, dark matter, dark energy, and false vacuum decay entered the picture. The story of symmetry grew darker. Each discovery revealed not stability, but fragility. The universe was not a fortress of immutable law. It was a tapestry of fractures, held together by balances that might shift again. The escalation is not only scientific, but existential. If symmetry shatters so easily, if the universe itself rests on imperfection, then permanence is illusion. We live suspended in a cosmos that could change in an instant, not by catastrophe from outside, but by collapse from within. The fear behind the mystery for physicists. The fear is not only the possibility of vacuum collapse or the unknown of dark energy. It is the deeper fear that symmetry, once thought to be the bedrock of reality, may never yield a final explanation. Each time we uncover balance, we find fracture. Each time we imagine stability, we discover fragility. Perhaps there is no ultimate symmetry, no final perfection to recover. Perhaps the cosmos is written not in balance, but in brokenness. The escalation of questions: why does dark matter exist? Why is dark energy so small yet so dominant? Why does the Higgs mass suggest instability? Why do neutrinos have mass at all? Why did inflation amplify fluctuations just enough to allow galaxies, but not enough to tear the universe apart? Each question traces back to the first moment, to the shattering of symmetry. And each question suggests that the mystery is deeper than we imagined, more unsettling than we dared to believe. The shattered truth, the escalation of discovery, leaves us staring at a haunting truth. The symmetry of the first moment was fragile, and its shattering echoes still. Inflation, dark matter, dark energy, quantum collapse, all are consequences of imperfection, of fractures in the fabric of existence. The symmetry that should have held did not. The universe exists in its brokenness, and that brokenness may not be finished. The first moment shattered. The shattering has not ended. The shattered symmetry of the first moment remains one of the deepest enigmas in physics. Matter should have vanished. Forces should have remained united. The universe should have dissolved into sterile light. And yet, here we are, in a cosmos, overflowing with galaxies, stars, and life. If symmetry broke, then the question becomes, how? Scientists have proposed bold theories, weaving mathematics and imagination into frameworks that might explain the imbalance written into existence. Each is an attempt to glimpse the fracture line running through the dawn of time. Baryogenesis. The origin of matter, the heart of the problem, lies barogenesis, the process by which matter triumphed over antimatter. Andrei Sakharov's 3. Conditions set the stage: baryon number violation, CP violation, and departure from thermal equilibrium. Several mechanisms have been proposed. One is electroweak baryogenesis, where the universe's cooling during the electroweak phase transition could have produced just enough imbalance. Another is leptogenesis, in which heavy neutrinos in the early universe decayed in CP ways, tipping the scales toward matter. Both ideas remain unproven, but they share a profound implication. The very reason we exist may be tied to rare processes in the first trillionth of a second. When symmetry cracked and matter was born, electroweak symmetry breaking, the role of the Higgs. The discovery of the Higgs boson in 2012 confirmed that a field permeates the universe, giving particles their mass. But this field itself is a product of spontaneous symmetry breaking at unimaginably high energies. Particles were massless, the electroweak force unified. But as the cosmos cooled, the Higgs field fell into a particular state, breaking the symmetry. Suddenly, particles gained mass, atoms became possible, and the universe's architecture was written here. Symmetry breaking is not a flaw, but a necessity. The fracture that allowed complexity to exist. Grand, unified theories. Symmetry shattered by cooling physicists dream of unifying the strong, weak, and electromagnetic forces into a single framework. A grand unified theory gut. In such a model, the early universe was governed by perfect symmetry. But as temperatures fell, this symmetry shattered, splitting into the forces we know. The breaking may have released heavy particles that decayed asymmetrically, fueling baryogenesis. If guts are true, then the fractured balance of today is the residue of a grander symmetry once whole. Our universe is the story of its unraveling. Supersymmetry, hidden partners. Another bold speculation is supersymmetry, Susie. The idea that every known particle has a heavier partner. If true, these superpartners could provide candidates for dark matter and new channels for symmetry breaking. Though the Large Hadron Collider has yet to find evidence for Susie, the theory remains tantalizing. Perhaps the early universe shattered a supersymmetry we can no longer see, leaving only traces in the abundance of dark matter. If so, then the visible world is but half of reality, the broken remnant of a more complete order. The multiverse, different, breaks, different laws. Some theories suggest that symmetry breaking may not be unique to our universe. If cosmic inflation is eternal, then countless bubble universes may exist, each with its own symmetry fractures, its own physical laws. In some, matter may have vanished. In others, forces may never have split. In ours, the shattering happened. Just so, allowing galaxies and life. This leads to the anthropic principle, the idea that we observe this universe simply because only here could observers exist. It is a sobering thought. Perhaps our cosmos is not inevitable, but one of many. Its balance of fragile accident, cosmic strings and topological defects. Some models predict relics of symmetry, breaking cosmic strings, domain walls, monopoles, defects in space-time itself, left behind like scars from the fractures of the early universe. So far, no such relics have been confirmed. But gravitational wave detectors and cosmic surveys continue to search for their subtle signatures. If found, they would be direct evidence of the shattering of symmetry, fossil traces of the first moment's fracture. The holographic and informational perspectives are the speculations. Step beyond traditional physics. The holographic principle suggests that the universe itself may be a projection from deeper laws. In such a picture, symmetry and its breaking may be emergent, the byproduct of information patterns rather than fundamental truths. If reality is informational at its core, then the first moment's fracture may be the origin not of matter alone, but of meaning itself. The split between possibility and actuality, encoded in the fabric of existence, the common thread from baryogenesis to supersymmetry, from guts to the multiverse, one theme binds them. Symmetry shatters to create reality. Balance is sterile. Fracture is fertile. The theories differ in mechanism, but they agree in essence. The perfection of the first moment could not last. It had to break, and in that breaking, the universe was born. The question beyond theories but speculation does not resolve the paradox. Each model explains fragments, none explains the whole. We still do not know why matter triumphed, why forces fractured as they did, why dark matter and dark energy emerged. Theories multiply, but the mystery remains. And perhaps that is the most haunting speculation of all, that symmetry breaking is not merely an event to be explained, but the fundamental nature of reality. The cosmos is fracture, writ large. The mystery of the first moment's shattered symmetry is not only a philosophical question, it is a scientific pursuit, carried out with the most ambitious instruments humanity has ever built. Each experiment, each observatory is an attempt to peel back the layers of time and glimpse the fracture that made everything possible. The tools are vast in scale and delicate in sensitivity. They reach from underground chambers shielded from cosmic rays to satellites orbiting Earth to machines that smash protons together at energies echoing the first trillionths of a second. All are directed at one purpose: to understand why symmetry failed and why the universe exists at all. The Large Hadron Collider, probing the Higgs and beyond. The discovery of the Higgs boson at CERN's Large Hadron Collider (LHC) in 2012 confirmed that spontaneous symmetry breaking gives particles their mass. But the Higgs may hold deeper secrets. Physicists are measuring its properties with exquisite precision, searching for deviations that could hint at new physics beyond the standard model. Does the Higgs couple differently to matter than predicted? Could it reveal hidden forces or undiscovered particles? Some speculate that the Higgs itself may be linked to baryogenesis, playing a role in tipping the balance between matter and antimatter. If so, then within the data of the LHC lies the answer to why anything exists at all: neutrino, observatorius, ghost particles, and CP. Violation neutrinos pass through the Earth in uncountable trillions every second, barely interacting with matter. Yet these ghostly particles may carry the key to cosmic asymmetry. Experiments such as Super Kamio Kondi in Japan, NOVA in the United States, and the upcoming Dune experiment are studying neutrino oscillations. They aim to discover whether neutrinos violate CP symmetry more strongly than other particles. If confirmed, this could explain baryogenesis. Neutrinos, invisible, elusive, may have tipped the scales in favor of matter during the universe's first second. The detectors themselves are marvels. Vast tanks of ultra-pure water or liquid argon buried deep underground, waiting for the faintest flash of light when a neutrino interacts. They are listening posts for whispers from the dawn of time. Cosmic microwave. Background missions. The blueprint of Symmetry, breaking the Planck satellite, has already mapped the CMB with extraordinary precision, revealing the seeds of galaxies in ancient fluctuations. But the next generation of missions, especially CMBs, will go further. These observatories will search for subtle imprints of primordial gravitational waves, ripples from inflation. They may also reveal traces of phase transitions in the early universe, when symmetries shattered and forces split apart. Every ripple in the CMB is a fossil of symmetry breaking. To map it more precisely is to read the blueprint of creation. Dark matter detectors. The shadow of symmetry deep beneath mountains and in caverns, shielded from radiation. Detectors such as Xenant, Luxeplan, LZ, and Pandex wait for collisions with dark matter particles. If dark matter was born in the fractures of the early universe, its detection would be direct evidence of symmetry breaking beyond the standard model. Its nature, WIMPs, axions, or something stranger would reveal. How deeply the cosmos's first imbalance shaped reality. So far, the detectors have been silent. But silence is not failure. It is a narrowing of the possibilities, a sharpening of the question. Gravitational wave observatories, listening for ancient fracture since 2015. LIGO and Virgo have detected gravitational waves from colliding black holes and neutron stars. But future observatories, such as LISA, will probe the universe at longer wavelengths, potentially hearing echoes from the earliest moments. If cosmic phase transitions produced gravitational waves as bubbles of broken symmetry collided in the infant universe, those waves may still ripple through space-time today. Detecting them would be like hearing the shattering of symmetry across 14 billion years. The sound of creation itself, the precision frontier beyond massive machines and cosmic observatories. There is another frontier, precision experiments. Measurements of the muon's magnetic moment at Fermilab suggest deviations from theoretical predictions, possible hints of new physics tied to symmetry violations. Experiments with rare decays, electric dipole moments, and quantum interference all search for cracks in the standard model's fragile symmetry. These are not grand collisions or cosmic maps, but delicate balances where the smallest deviation may reveal the fracture line of reality, the horizon of future tools. The next century of physics will sharpen these efforts. Proposed future circular colliders, larger than the LHC, could probe energies far beyond today's reach. Neutrino observatories like Hyperkamiokande will extend sensitivity. Space-based missions will map the CMB and measure dark energy with unprecedented clarity. Each tool is an attempt to hold a mirror to the first moment, to see the reflection of symmetry before it shattered, and to understand why it did, the limits of the search. But even as tools multiply, a sobering truth emerges. Some answers may forever be beyond reach. If the breaking of symmetry occurred at scales beyond what colliders can probe, or if the multiverse is real, then the evidence may lie forever outside our horizon. Science may map the consequences of broken symmetry, but never touch its origin. The fracture line may remain hidden, written into existence, but unreachable, the human dimension, and yet the pursuit continues. These machines are not only instruments of physics, they are instruments of longing, of humanity's refusal to accept ignorance, of our hunger to know why the cosmos exists at all. In their tunnels, in their detectors, in their orbiting eyes, we are reaching back to the first instant, Asking the same question, the stars themselves seem to whisper, why was symmetry broken? The search may never end. But in the search itself lies meaning, a direction in a universe born of fracture. The journey into the shattered symmetry of the first moment leads not only to physics, but to philosophy. It is a story written in equations and detectors, but also in metaphors and meaning. For in the fracture that broke perfection, we glimpse not only the origin of matter, but the paradox of existence itself. Symmetry, as the dream of perfection symmetry, has always held a special power in the human imagination. From the spiral of seashells to the geometry of snowflakes, from the architecture of cathedrals to the equations of physics, symmetry has symbolized order, beauty, and perfection. To imagine the first moment of the universe as perfectly symmetrical is to imagine the ultimate order, a cosmos poised in flawless equilibrium. But perfection, in this sense, is sterile. A universe of perfect balance would have annihilated itself in an instant. Matter and antimatter erasing one another, forces never diverging, structure never forming. The dream of perfection contains within it the possibility of nothingness. Brokenness. As creation, it is only in imperfection that creation becomes possible. The tiniest imbalance between matter and antimatter, one particle in a billion, meant survival, meant stars, meant life. The collapse of unified forces into distinct interactions gave rise to chemistry, to biology, to thought. Broken symmetry is the fertile soil of reality. The cracks are where being emerges. This truth is unsettling because it overturns our ancient intuitions. We seek perfection, but the universe thrives in imperfection. We imagine balance as ideal, but existence depends on imbalance. To live in such a universe is to recognize that creation itself is born of fracture. The fragility of reality, the revelations of modern physics deepen this paradox. The Higgs field may place us in a false vacuum, one fracture away from annihilation. Dark energy, mysterious and uniform, accelerates the cosmos toward emptiness. Inflation suggests that universes may bud endlessly, each shaped by a different shattering of symmetry. Our existence, then, is not only the product of imperfection, it is precarious. We live balanced on the edge of brokenness, dependent on asymmetries, whose origins we cannot yet explain, whose future we cannot predict. The fragility of reality is not an abstraction. It is our condition, the mirror of human life. There is a strange resonance between the universe and the human experience. Just as cosmic perfection would have yielded nothingness, so too would a perfectly ordered life. It is in imperfections, in fractures, struggles, and asymmetries that growth and meaning emerge. Each life is a microcosm of the universe, not balanced to perfection, but shaped by its brokenness. Our choices, our histories, our very individuality depend on asymmetry. If symmetry had held, there would be no us. In this sense, the shattered symmetry of the first moment is more than a physical mystery. It is a metaphor for existence, itself the paradox of explanation, and yet the question remains unanswered. Was the shattering of symmetry chance, necessity, or design? Did it occur by accident, or is it written into the mathematics of reality? Science may never know. Some answers may be hidden beyond experimental reach, locked in scales too vast or energies too high. The multiverse may mean that our universe is one among countless others, each with its own fractures, each unobservable from the rest. Perhaps the greatest paradox is this: the question of why symmetry broke may be forever unanswerable, and yet it is the reason we can ask it at all. The poetic vision, imagine again the first moment, a mirror, whole and flawless, poised in silence. Then a crack, the symmetry shatters. In the shards, galaxies form. In the fractures, stars ignite. In the imbalance, life awakens. We live inside that broken mirror, in a universe built of imperfection. And it is precisely this imperfection that gives us the ability to see, to think, to wonder. The symmetry broke, and in that breaking, the cosmos began to sing. The final reflection, the shattered symmetry of the first moment, is not only a scientific puzzle, but a profound lesson. Perfection may be beautiful, but it is sterile. Brokenness may seem flawed, but it is creative. The cracks are where the light enters, where existence emerges. The haunting truth is that without the fracture, nothing would be. Without the asymmetry, no stars would burn, no planets would form, no minds would ask why. The universe exists because perfection failed, and in that failure lies its greatest triumph. Closing imagery, look up at the night sky. Each star, each galaxy, is a fragment of the first shattering. Each glimmer is a reminder that the universe is not whole, but broken, and that its brokenness is its glory. The symmetry of the first moment may never be recovered. The fracture may never be explained, but in its mystery lies meaning. For to live in such a universe is to live in a cosmos where imperfection is not error, but the essence of creation. The mirror cracked, and in the cracks we found our home.